So this is part 2 of L'Hopital's rule, and previously we talked about indeterminate forms being 0 over 0 or infinity over infinity. And it turns out there are other indeterminate forms, such as 0 times infinity, infinity minus infinity, 0 to the power of 0, infinity to the power of 0, and 1 to the power of infinity. However, L'Hopital's rule only applies to the indeterminate forms 0 over 0 and infinity over infinity. Therefore, we must manipulate functions to get them into the form 0 over 0 or infinity over infinity before we can apply L'Hopital's rule. So let's see some examples of that. In example 3 here, we're asked to find the following limits. And for this first limit here, as x goes to infinity of x times tangent of 1 over x, if I used direct substitution, I would end up getting infinity times tangent of 1 over x as x goes to infinity. That's going to be tangent of 0, which ends up equaling 0. And 0 times infinity was one of our alternative indeterminate forms. So what we want to do is we want to get this into looking something different. And right now, I have the limit as x goes to infinity of x times tangent of 1 over x, and I can rewrite this thing as tangent of 1 over x over, I'm going to change this x here and bring it to the denominator and rewriting it as 1 over x. In other words, I took the reciprocal of it. And notice that if you take the reciprocal of 1 over x and multiply it to tangent of 1 over x, that will return our original function that we were looking at. So now if I were to use direct substitution, I would get the indeterminate form 0 over 0. And now I can apply L'Hopital's rule like we've been doing. And so I want to take the derivative of tangent of 1 over x. So that's going to be secant squared of 1 over x. And then I need to use chain rule and multiply by the derivative of the inner function, which is going to be negative 1 over x quantity squared. And then from here, I want to take the derivative of our denominator, which is 1 over x. And if I took that derivative, it would give me negative 1 over x squared. So notice that negative 1 over x squared appear in both the numerator and the denominator. And so if those divide out, we get that this limit simplifies to the limit as x approaches infinity of secant squared of 1 over x. And now what happens is 1 over x, as x gets really large, this essentially turns into secant squared 0. And that's the same thing as 1 over cosine squared 0. And cosine of 0 is 1. And so we get that our final answer for part A is 1. Part B asks us to find the limit as x approaches 1 of x over x minus 1 minus the fraction 1 over the natural log of x. And if I used direct substitution on this, I would end up getting 1 over 0 minus 1 over 0. And 1 over 0, if your denominator gets really, really, really small or approaches 0, essentially another way of thinking about this is of the form infinity minus infinity. And that's one of our alternative indeterminate forms, but we need to get it so that it's either in the form 0 over 0 or infinity over infinity. So in this case, what we want to do is notice that we're subtracting two fractions, and I want to find a common denominator. So I'm going to rewrite my fractions. So I have x over x minus 1. I'm going to multiply that by the natural log of x over the natural log of x. And this is again in the effort to find a common denominator. And my second fraction, I'm going to multiply that by x minus 1 over x minus 1. So my new combined denominator is going to be the natural log of x times the quantity x minus 1. And then my numerator is going to become x times natural log of x. And I'm going to distribute this negative 1 into the x and the minus 1. And if I do that, I get minus x plus 1. And now let's go ahead and use direct substitution to see what happens. So if I plug in 1 for all of my x's, the natural log of 1 is 0. So essentially, if you simplify this, we're going to get 0 over 0. And that's one of the indeterminate forms that we want. So let's go ahead and use L'Hopital's rule now. For my numerator, I'm going to need product rule. So I have the first function times the derivative of the second function plus the second function times the derivative of the first function. Then I'm taking the derivative of negative x, so that's going to be minus 1. And then the derivative of plus 1, that's a constant, so that derivative would be 0. Now we want to take the derivative of our denominator, and we have to use product rule again, because I have the natural log of x times the function x minus 1. So if I'm using product rule, I have the first function times the derivative of the second function plus the second function times the derivative of the first function. Let's do some algebraic simplification. So the x times 1 over x, that's going to become 1, plus the natural log of x minus 1 over the natural log of x, and I'm going to distribute 1 over x into both of these terms. If I do that, I get plus 1 minus 1 over x. And notice that this 1 and this minus 1 are going to cancel out. And if I use direct substitution at this point, I would get 0 over 0 once again. And so we're going to use L'Hopital's rule another time. The derivative of the natural log of x is 1 over x. And then the derivative of plus 1, that's a constant, so that's going to be 0. And the derivative of minus 1 over x, that's going to become plus 1 over x squared. And it looks like we're going to be able to use direct substitution now. If I use direct substitution, we would get 1 over 1 over 1 over 1 plus 1 over 1 quantity squared. And the numerator is going to simplify to 1, and then the denominator would end up simplifying to the number 2. So finally, we get that our limit is 1/2.